Hello everyone, welcome to a new lecture of our course on heterogeneous systems. Today we are going to continue not with a new parallel pattern, but with an advanced optimization technique that can be applicable to multiple parallel patterns. In particular, we are going to focus on matrix multiplication, which, as you know, is a key primitive for many machine learning workloads, including convolutional neural networks that we introduced in the previous lecture. Before we go into the details of this advanced tiling for matrix multiplication, let me very quickly recap on what we have covered so far regarding parallel patterns, the part of the course that we started after giving the basics of GPU programming. In these parallel patterns, we started with the reduction operation. That is an operation that reduces a set of values to a single value. The properties of reduction are associativity, commutativity, and identity value, and reduction is a key primitive for parallel computing. The way of implementing an efficient reduction on GPU is to have active threads that belong all to the same warp. This way, we can implement a divergence-free mapping and maximize the warp utilization. The second parallel pattern that we covered in the course was histogram calculation, which is frequently used for reducing the dimensionality and extracting notable features of large data sets. In a basic histogram, what we do for each element in the data set is to identify what's the corresponding bin, the corresponding element of the histogram, of the output histogram, and increment it. When computing parallel histograms in parallel, we need to use atomic operations. And the problem with atomic operations is that they cause serialization. We need to use atomic operations because we will typically have multiple threads accessing the same histogram. If we want to deal with the drawbacks of serialization, we can apply different optimization techniques. For example, privatization that essentially assigns one local histogram or a subhistogram to a number of threads, for example, a thread block. The next parallel pattern that we covered in the course was convolution, a widely used operation in signal processing, image processing, video processing, and computer vision. In convolution, what we do is applying a filter or a mask on each element in order to calculate a weighted sum of a set of neighboring input elements. This convolution is especially important these days in machine learning and artificial intelligence, and in particular in the convolutional neural networks or CNNs. Remember, convolution, we started with the example of 1D convolution, where we have a linear array, and on each of the elements of this input array, we apply the mask or the filter, we obtain some partial products, and then we sum all these partial products in order to obtain the final value that will go to the output array. Very similar is how we calculate the 2D convolution, which is more useful for CNNs. In this case, the CNN filter is, the convolution filter is a two-dimensional filter. In this particular example, is a 5x5 filter. As you can see, we place the filter on top of each of the elements of the input layer of the input feature map, and then we will obtain some partial products and then compute the final reduction to obtain the element of the output layer or the output feature map. Remember as well that in the previous lecture, we mentioned that convolutional layers can be reduced to matrix multiplication, and the way of doing so is by unrolling the input feature maps. As you can see from these three input feature maps, we are obtaining this matrix of unrolled input features. We are going to go in more detail about how to do this unrolling and about how to do this reduction of the convolutional layer into the matrix multiplication. And after that, we are going to see in detail how to optimize the execution of this matrix multiplication. So that's why now we start this part of the lecture called efficient CNN on GPU. Remember that a CNN, a convolutional neural network, is a neural network with convolutional layers combined with other types. And a very good example is LeNet5, a CNN for handwritten digit recognition. The CNN is composed by multiple layers, and that these different layers have different characteristics. For example, the initial convolutional layer of LeNet5 uses 6 filters of 5 by 5 pixels. As a result, we are going to obtain 6 output feature maps that are these C1 feature maps that you can see on the slide. But the characteristics of the different layers change. Even though some of them will still be convolutional layers, but the number of filters that we are going to use in the different layers might change, right? So, for example, here, this layer here, we are using 96 filters of 5 by 5 pixels in total, but these filters are used in groups of 6 because that's the number of input feature maps. So this is going to be the same as doing a 3D convolution of a 14 by 14 by 6 pixel input with 16 filters of 5 by 5 by 6 pixels each, because we have the filters are grouped in groups of 6, as you can see in the figure. For an example of a convolutional layer, we go back to the same example that we used before. Remember that here we have our input feature maps. In particular, we have 3 input feature maps in this example. The size of these input feature maps is N1 times N2 pixels each. In this specific example, N1 and N2 are both 3. Then we have the convolutional filters, W, and the size of these convolutional filters is K1 times K2 pixels each. And in this particular example, both K1 and K2 are equal to 2. And by applying the convolution filters over on the input feature maps, we obtain the output features. The size of the output features, the output feature maps is N1 minus K1 plus 1 times N2 minus K2 plus 1. Because in this particular example, N1 and N2 are equal 3, and K1 and K2 are equal 2, the final size of the output feature maps is 2 by 2, as you can see. One interesting observation in this convolutional layer is that there is a lot of data parallelism, because we are applying the same computation on all the pixels of the input feature maps. So all output feature maps or all pixels of the output feature maps can be calculated in parallel. So one strategy to implement a convolutional layer on a GPU would be to launch a single kernel to calculate all pixels of all output feature maps, and each thread block can calculate a tile of the output feature map pixels. For example, a tile of one of the output feature maps. So essentially, we are going to have a collection of summation of 2D tile convolutions. If you want to see in more detail how to do this, I would recommend you to go to chapter 16 of the book, Programming Massively Parallel Processors. So one possible design of this basic kernel is to have each block compute a tile of output pixels. We are going to have tile with pixels in each dimension. So that's going to be the dimension of the tile. Tile width is either the, let's assume for now that that is either the height or the width of the of each of these tiles. And the kernel is going to make use of a grid of thread blocks, and one potential way to map computation onto these thread blocks is using a 2-dimensional grid where the X dimension maps to M output feature maps and the Y dimension maps to the tiles of each of the output feature maps. So as you can see here, we would be linearizing each of the computation of each of the output feature maps, because even though the tiles might be 2-dimensional, we are assigning a single dimension, the Y dimension of the grid, to all tiles that belong to and all thread blocks that will compute these tiles of each of the output feature maps. So some observations about this potential implementation: the amount of parallelism is quite high, as long as the total number of pixels across all output feature maps is large. For early stages, there are fewer but larger output feature maps. So there is a large Y dimension. There are not so many output feature maps, but these output feature maps are larger. And typically, for later stages, the feature maps become smaller, but there are more. So we have a large X dimension. So in this scheme, as you can see, keeps the number of threads more or less stable across the stages. And that's something pretty interesting when it comes to implementing an entire neural network onto the GPU. More observations is that each input tile is loaded from global memory multiple times by multiple blocks. And once for each block that calculates the output tile that requires the input tile. So this is not very efficient in terms of global memory bandwidth and becomes more of a problem when the output feature map become small or increase in number. So one way of optimizing these convolutional layers is reducing them to matrix multiplication. Convolution layers are the most compute-intensive parts of a CNN, and GPUs are extremely good at doing matrix multiplication. There are very high performance implementations of matrix multiplications for GPU, because there are very good tiling techniques, very advanced tiling techniques for matrix multiplication that naturally reuse the input features across output feature maps. And these tiling techniques are the ones that we are going to discuss in a few slides. So the idea here is to convert convolutions in a convolution layer to a matrix multiplication in order to help keep the level of parallelism stable across the CNN layers. So what we are going to do is, first of all, we need to unroll the input feature maps in order to obtain this matrix of unrolled input features. We would also have to do the same for the convolution filters, but as you see, this is indeed simpler because each of the rows of this matrix of convolution filters corresponds to the three filters, the three green filters that we have here on the left-hand side of this convolutional layer. However, when it comes to unrolling the input feature maps, one thing that we should observe is that some of the values in the unrolled matrix of input features are replicated. And we need to do that because the way that the convolution filters are applied on the input feature maps is by repeating the elements that are being used to obtain one element in the one pixel in the output feature maps. A function that generates the unrolled matrix of feature maps or of input feature maps is going to look something like this. Something that we can already identify here is the number of channels or the number of input feature maps. We also have the height and the width of each of these input feature maps. K is the dimension or one of the dimensions of the filter, and this X is the collection of input feature maps, and this X unroll is going to be the output of this unroll function, of this unroll kernel, that is the unroll matrix of feature maps. We are going to take a closer look at this code, but we are going to see it in the context of the actual transformation that happens. Remember that when it comes to unrolling, the four elements that are here that need to be used for calculation of one output pixel need to be unrolled, as you see. So this 1, 2, 1, 1 will go here, 1, 2, 1, 1. These four elements 2, 0, 2, 0, 2, 0, 1 are here, 0, 2, 0, 1 are here, and these four elements are here. If we look at the second column, if we look at the second column of the unrolled matrix, what we see is that these elements here, 2, 0, 1, and 3, correspond to this tile of the input feature map, 2, 0, 1, 3. And these 4 elements of the second column correspond to these 2, 1, 1, 2. So those are, this is how the matrix, the unroll matrix, is generated. And that's what we do with this code. As I said earlier, C is the number of input feature maps, is 3 in this example. K is 2 in this example, because in this simple example, the convolution filters are square and they are 2 by 2. And finally, the outputs are H out and W out that are both equal to. Those are the dimensions of the output feature maps. So if you look at the code, as you can see, we go channel by channel. So we unroll each of these input feature maps in successive iterations. And the very first thing to calculate is this W base. As you see, W base is a function of the number of the channel, the number of the input feature map, and the dimensions of the filter, K by K. So with this W base, what we are actually doing is placing a pointer to one specific element in each of the columns. For example, in this first column, if C is equal 0, because we are unrolling this first input feature map, W base is going to point here. If C is equal 1, because K by K is 2 by 2, is 4, this W base is going to point exactly here. And if C is equal 2, because K by K is 4, this W base is going to point exactly here. So now we know what's going to be the row in the unrolled matrix of input features. The next thing to do is to actually unroll the corresponding tile, and observe that because the size of the tile is the same as the size of the convolution filter, is K by K, we have to go this way. We have to go first, the first row of the tile, then second row of the tile. This is how we will go with these four nested for loops that we have here. So next thing is to calculate what's the age, what's the column in the unrolled matrix for each individual element. No, sorry, it's not the column, it's this the exact row in the unrolled matrix of each individual element, starting from W base that we calculated earlier. And the exact place where we are going to put each of these 4 elements of the tile of the input feature map is given by these indices P and Q that tell us to what element we are exactly referring to, right? And based on that, if we are in the C equals 0, because we are in the first input feature map, this H unrolled is going to be equal to 0, 1, 2, or 3. If C is equal 1 and we are unrolling this tile, this H unrolled is going to be equal to 4, 5, 6, 7. And now to obtain or to calculate the last, the second index that we need to access the unroll matrix, we need this W unroll. And this W unroll is given by H times W out plus W, because the exact column where one specific value is going to reside, where one specific pixel of the input features is going to reside, depends on the specific element of the output feature maps that we are calculating. So that's why we have these 2 nested loops that go through H and W being H and W, the dimensions, the indices, the row and the column of the output feature map. So this W unroll is equal to H times W out plus W. That it tells us that the specific element that we are, the specific element that we are calculating here in the output features depends on the specific position that they originally had in the output feature maps. And this is how we obtain the column of the unroll matrix of input features. So this X unroll is for these indices, H unroll and W unroll is obtained by accessing the corresponding element of the original matrix X or tensor X that contains the non-unrolled input feature maps. So this is the way of turning or unrolling a convolutional layer into a matrix multiplication. And now we are going to see how we need to operate in order to execute the matrix multiplication efficiently on a GPU. We all are familiar with simple matrix multiplication. In matrix multiplication, each product matrix element is an element of the output feature map pixel. And in order to calculate each element of this output feature map, we need to perform the dot product of a row of the convolution filters in this case, and a column of the input feature maps, as you see. So in order to obtain this 14 here, we need to calculate the dot product between this row and this column. So let's start with a very simple example, with a toy example, where we use a 2x2 tile in shared memory. Each block calculates one 2x2 output tile, so 2 elements from each output map. So each thread block needs to first load one 2x2 filter tile and one 2x2 input tile into the shared memory and perform 2 dot product steps for all its 2x2 output elements. So for example, the red thread block that has been assigned this red tile will have to load this tile from the input feature maps into the shared memory, and this other tile from the filters, from the convolution filters matrix into the tile, and then perform the dot product operation of these 2 elements with these 2 elements, and these 2 elements with these 2 elements. So as you can see, each input element is reused 2 times in the shared memory, because these 2 elements, this one here and this one here, are used to calculate this value and this value. This implementation of matrix multiplication is something that we have covered already in this course. Remember that in one of the initial lectures, we explained how to do the tile matrix multiplication using shared memory, and what we do in order to calculate, for example, this tile of the output matrix C is to first of all load each tile, load the first tile of each matrix into the shared memory, and we load this tile, and then we also load this tile, and then once they are in shared memory, we can compute the partial dot product of the elements of this tile and the element of this tile, and obtain these partial results for these elements of the tile of matrix C. Let's now see another example, because the size of the tiles doesn't need to be fixed. In the previous example, we had a 2x2 tile. Here, we are going to consider a 2x4 tile in shared memory for the output. So this is the output tile, 2x4, and in this case, the thread block that is assigned this 2x4 tile will need to load into the shared memory a 2x2 filter tile, which is the orange one, and then a 2x4 input tile that is the red one. Then it performs the partial dot product steps and obtain partial results for these elements or these pixels of the output feature maps. So as we can see here, each input element is reused 2 times. Each element of the input feature map is reused 2 times after having loaded it into the shared memory. And it's 4 times for the elements of the filters, because these 2 elements are going to be used to calculate this 14, this 20, this 15, and this 24. So there is more reuse in the case of the filters. So the size and the dimensions of the tiles determines how much reuse there's going to be. But one important analysis that we need to do is an analysis of efficiency in terms of memory space that is due to the replication that is needed when we are enrolling the matrix of input feature maps. So each output map element requires its own replicated K by K input feature map elements, not replicated for different output feature maps. There are H out times W out output feature map elements. So each one requires K by K replicated input feature map elements. So the total number of input elements after replication is H out times W out times K times for each input feature map. So the total number of elements in the original input feature map is H out plus K minus 1 times W out plus K minus 1. So as we see, we have more elements in the unrolled and output feature map, the input feature map. So this is what we call the expansion ratio, the ratio between the elements that we have in the unrolled matrix of input features divided by the elements that we had in the original input feature maps. In our example, where H out is 2, W out is 2, K is 2, there are 3 input maps or 3 channels. The total number of input elements in the replicated unrolled matrix is 3 by 2 by 2 by 2 by 2. The expansion ratio in this case is 3 by 2 by 2 by 2 by 2 divided by 3 by 3 by 3. And this is in total 1.78. So this means that the size of this matrix of unrolled matrix of input features is 78% larger than the size of the original input feature maps. This is a drawback, but there are advantages from doing this. Tile matrix multiplication is that it's more stable in matrix sizes. For example, each filter band, the filter band matrix is an M times C times K times K matrix, where M is the number of output feature maps, and the expanded input feature matrix is a C by K by K by H out by W out matrix. So the sizes of the matrices depend on the product of the parameters to the convolution and not the parameters themselves. That has something good. For example, while H out and W out tend to decrease towards later stages of a CNN, C, the number of channels, tends to increase at the same time. So what this makes is that the amount of work of each kernel launch, the amount of work in each layer will remain more or less stable or will remain large and stable as we go to the later stages of the CNN. More important details about unrolling the input feature maps. One interesting thing, and this is what actually happens in real implementations of convolutional layers, is that the conversion from convolution to matrix multiplication doesn't need to be done in advance. It doesn't need to be a pre-processing before performing the matrix multiplication. It's something that can be done during execution. So the input feature maps are in memory stored in the original form, and the kernel that implements the convolution layer also performs the unrolling on the fly. So it accesses the input feature maps as they are originally stored in the original form, accesses them using similar addressing as the one that we have seen in the previous example, in the previous unroll function that we explained. But it's performing these accesses on the fly. It's performing this unrolling on the fly. So we don't need to pay for the pre-processing cost that comes from unrolling the matrix. So that could have been a big issue if we had to pre-process, but we can make use of this special addressing in order to access the data in the way that we need to perform the matrix multiplication, and this way perform the enrolling on the fly and save a lot of memory space. So now that the way of transforming a convolution layer into a matrix multiplication is clear, now we are going to go into the advanced tiling techniques for matrix multiplication. This is something that we somehow explained briefly in the previous lecture. We are going to cover it today with more detail. This is what we call the joint register shared memory tiling. Registers are extremely high throughput. They are closer to the GPU execution units, to the SIMD units that execute the instructions in the GPU cores, but they have the disadvantage that they are private to each thread. So that's why register tiling usually needs to use thread coarsening, because if we really want to create a tile using registers, we have to assign more elements to the same thread, and these elements will go into multiple registers assigned private to each thread. On the other side, we have shared memory that is accessed at lower throughput than registers, but it's still much higher throughput than global memory. The advantage of the shared memory is that it is visible to all threads in the thread block, and that's why we don't need to necessarily do thread coarsening. But it has the drawback that in order to write something into the shared memory, we first need to read it from global memory, put it into registers, and then from the registers write to the shared memory. That's the traditional way of doing it. Remember that in a previous lecture, we also mentioned that in the A100 GPU, there are asynchronous load instructions that allow us to bring data directly from the global memory to the shared memory without using registers. And that's even more advanced in the newer H100 architecture. But in principle, we have to go through the registers to do this movement of data, or movement of a tile between global memory and shared memory. We typically use both registers and shared memory for tiling different dimensions of multidimensional data, and that's what we are going to see in the next slides. The use of the registers can be even more sophisticated, more aggressive with word programming and tensor cores that we also introduced in the previous lecture. So let's talk about the data reuse in matrix multiplication, because this data reuse is what justifies the use of tiling. When it comes to calculating elements of the output matrix P, and we have two input matrices, M and N, you can see that in order to compute the elements of the output matrix P, we have to access each of these elements of the output matrix P. We have to access one entire row of M and one entire column of N. Now imagine that we are going to have one different thread calculating each of these four highlighted elements of matrix P. For example, thread 1 or T1 here, T2 here, T3, and T4. So what we see is that this row of matrix M is entirely accessed by T1. This row is entirely accessed by T2. But at the same time, all these elements of this column are accessed by the four threads, T1, T2, T3, and T4. They all need these elements of this column in order to calculate the elements of the assigned elements of matrix P. So as you see, we have reuse of column data in N. Now we could assign threads to the elements in a row of the matrix P. So we would have one thread here, another here, another here, and another here. All these different columns are accessed by different threads, but all the elements of this row of matrix M are accessed by all threads computing elements of this row of matrix P. So this shows the reuse of raw data in M. So in the end, we have reuse on both. We have reuse on matrix M, we have reuse of elements of matrix N, and that's why we are going to exploit the tiling. So in each iteration of the algorithm, we are going to use 4 elements of matrix M, these 4 elements, and 4 elements of matrix N in order to calculate partial results for these 16 elements of matrix P. The tile of the output matrix doesn't need to be a square. It was a square in this figure, but it doesn't need to be a square. And here in this example, we have a 4x2 tile, right? So in each step, in each iteration of the matrix multiplication algorithm, we are going to use 4 elements of M and 2 elements of N. That will be step 1 or step 0 or index I equals 0. In the next step, in step 2, we have to go to the next bunch or the next set of 4 elements of M and the next set of 2 elements of N. And in the next step, we read 4 more elements of M and 2 more elements of N. So as you can see, for a 4x2 tile, only 6 elements need to be loaded for all 8 threads of the tile, the threads that they are computing these output elements, for all these threads to make progress. If the tile is 4x4, we will need 8 elements in total for the 16 threads. We will need 4 elements from matrix M and 4 elements from matrix N. So in the kernel of the previous slide, and assuming that we are using the 4x4 output tile, observe that we have tile with square elements of M and tile with squares elements of N that are loaded into the shared memory. Remember that this is how we used to compute matrix multiplication, loading one tile of elements of matrix M into the shared memory, another tile of elements of matrix N into the shared memory, and then we start performing the computation, right? So each thread block calculates tile with steps for tile with square elements of P. And this tile width is typically something like 16, or at least something like 16. So according to our analysis, we can use much smaller amount of shared memory if instead of loading entire tiles of M and entire tiles of N, and these tiles are 2-dimensional tiles of tile width square, tile width square, if we only load tile with elements of M and tile with elements of N in order to calculate one step for the entire two-dimensional tile of the output matrix. But why we didn't do so? The reason is that if we load the smaller tiles, we will have to synchronize more frequently, right? In each iteration of the output loop, outer loop, we'll have to load a subset of threads. So we will have to have a subset of threads of the thread block, loading elements of M, tile with elements of M, and then tile with elements of N, and load them into the shared memory. This first has the problem that we have many more threads in the thread block, tile with a square threads in the thread block, right? So some of the thread blocks will do nothing. So that's why we have divergence and load imbalance. So, and after performing these loads, we have to call syn threads. Then all threads calculate one step of the inner product, the inner loop that generates to one iteration in this case. And we call again syn threads before we load the next set of elements from M and N. where we go to the next iteration. And even though sync threads is pretty efficient on these GPUs, but its intensive use is still going to hurt the performance. So that's why it makes more sense to use this joint register shared memory tiling. In the example that we are going to cover, we are going to use tile width M and tile width N are going to be different. The size of the tiles, the dimensions of the tiles. So basically the tile is not a square. In this particular example, tile width M is equal to 4 and tile width N is equal to 2. And we are going to use 8 threads in total to compute this 4x2 tile of matrix P. We store input M tile and output T tile elements in registers. So all these elements of P are in registers, and all these elements of M are also in registers, while the elements of matrix N, the tile of matrix N, is going to be stored in shared memory. As you see, we now decouple M and N. The input tile widths of M and N, they don't need to be the same size. And in our example, they are different, 4 and 2. And there are some key quantities here. The number of threads that we are going to use in this example is tile width M. So it's actually 4, even though the output tile is 4x2. So the output tile has 8 elements. We are going to use a thread block of only 4 threads. And the way that we assign these threads is 1 thread per each of these rows of the tile of P. So thread 0 starts computing here, thread 1 starts computing here, thread 2 starts computing here. Another important quantity is the output tile size that we already know is 4x2, is tile width M times tile width N. The number of reuses for each element of N, is going to be reused 4 times in our example, tile width N, tile width M, because this element, we use it to compute this element, this element, this element, and this element of the output tile P. The number of reuses of each M element is tile width N. So this element here, thread 0 is going to use it to compute this element and to compute this element. So each thread computes tile width N elements of P. Thread 0 computes this element and this element. So in total, 2. This is the basic of the joint register and shared memory tiling. We can observe that there are 2 key optimizations here. The first one is thread coarsening, because we have each thread to calculate a horizontal strip of the tile, or a horizontal row of the tile. This strip has in total tile width N elements, 4 in this figure, 2 in the figure of the previous example, of the previous slide. And the data loaded from M can be reused tile width N times through registers. So this is why we talk about register tiling, because we are storing this element of M in registers and all these elements of the output matrix P in registers as well. So we load this value from M into a register, R1, and then we can use it for up to 4 times in order to compute 4 intermediate results for matrix P. Now the second optimization is shared memory tiling here, because we store one entire tile of matrix N into the shared memory. We are going to have multiple threads of the thread block. Remember that in this example, we are using 4 thread blocks that will calculate this horizontal strip, thread 0, this horizontal strip, thread 1, this one, thread 2, and so on. And these multiple threads are going to collaborate to load one this tile of size tile width N, of elements of N, into the shared memory. So T1 to T4 or T0 to T3, depending on how you want to index them, cooperatively load 4 values of N into the shared memory for later use. So in one iteration, each thread first accesses one element from register, one element of M from registers, and then accesses tile with elements of N of the matrix N from shared memory. So thread 0 performs partial calculations for these 4 elements of matrix P by accessing these values here in one register, and then accessing these 4 values here from shared memory. So it calculates one step of 4 tile with N elements of P. And these intermediate results computed by this first thread are stored in registers. The size of this tile with N is typically something around 16 in practice, and it's it might be larger as well, but in the end there is a limitation due to the number of available registers in each GPU core. So 16 seems something reasonable, but of course, if you are implementing these joint register shared memory tiling, it's good to experiment with different values for tile with N and tile with M in order to tune the performance of the kernel. So in one iteration, each block has a tile of size, has tile with M threads, 64 or more in practice. Remember that these threads are assigned to each of these horizontal strips. So thread 0 starts here, thread 1, thread 2, and thread 3. Loads tile with M, elements of M into registers, and loads tile with N, elements of N, into the shared memory, as we discussed earlier. We need tile with N threads in order to load the tile of matrix N into the shared memory, but also remember that we are applying thread coarsening. So what this means is that in the end, we are kind of folding tile with N threads into a single thread, because one single thread is going to compute all these elements tile with N that that belong to each of the horizontal strips of the tile. Problem that we have is that when it comes to loading data from the global memory to the shared memory for matrix N, we may not need all threads, all available threads to perform this loading. And that's something that we can clearly see in this example, because the number of threads of the thread block is 4, is tile with M, and this is larger than 2, that is the tile with N, the number of elements that we need to load in shared memory. So not all threads are active, right? A way of making this approach more balanced is to have threads loading more than what is needed in each individual iteration, in each step. So now what we do is that in each iteration, all threads in the block collaborate to load tile with N times K elements of N into the shared memory. So now we are loading an entire tile, not just a single row of the tile of N. We load a 2-dimensional tile into shared memory, and the size of this tile is given by tile with M indeed. So K is said in a way that tile with M, which is the number of threads that we are really using in the thread block, is equal to tile with N times K. So this way, every thread loads one element of M, and there is no divergence. And each thread as well loads K elements of M into registers. So we are going to need more registers for each thread. In total, K registers for each thread. So in the beginning of each iteration, we will have the threads, the tile with M threads go into global memory, bringing a tile of matrix N into the shared memory, and then this tile with M threads will go to global memory and will bring k elements to their own registers, k elements of m to their own registers. And this way, in each iteration, we are in reality calculating k steps of the multiplication, because we can go over the k elements that we loaded here. Imagine that k is equal 2 or k is equal 4, for example. We go over the k elements here, same as we go over the k elements here, to compute partial results for each of these elements of the matrix output matrix P. So each block calculates k steps for tile width n times tile width m elements of P. In each iteration, the thread block calculates k steps for these elements of the output tile. So as a summary, each block has tile width m threads. Each thread is coarsened by tile width n times, because each thread calculates tile width n elements of the output matrix. Each thread loads one n element into the shared memory, one element of n into the shared memory, and also loads k elements of matrix M into their own registers. And this way, they can calculate k steps for the elements of P. In our toy example, we can make tile width M equal 8. So in total, we're going to use 8 threads. Tile width N equal 4. So that's the width of the tile of matrix N. Each thread block has 8 threads. Each thread is coarsened 4 times. So each thread loads 1 element of N, 2 elements of M, which, because k in this example is equal 2, and this way we can calculate in each iteration 2 steps of 4 elements of, or each thread calculates 2 steps of 4 elements of matrix P. This technique was proposed back in 2008 by Volkov and Demel, and they implemented it for GTX 2080. In their implementation, each block had 64 threads, so tile width M is equal 64. Each thread coarsened by 16 times, so tile width N equal 16. And this way, each thread loads 1 element of N, 4 elements of M into registers, and then calculates k steps, 4 steps of 16 P elements. We can compare this implementation with the joint register shared memory tiling with the tile SGEM that we initially explained in this course for matrix multiplication, where both tiles are go to the shared memory and are used there. And if we have so for thread block, so has 32 threads. The total of the thread block can calculate. No, sorry, because here the thread block has is a 32 by 32 tile, so in total 1024 threads. So that means that each thread block computes a tile of 1024 elements of the output matrix, and in total it needs to use 12 kilobytes of on-chip memory, including registers and shared memory. Compared to the register shared memory tile version of SGEM, each thread block computes 64, which is the number of threads in the thread block, times 16, which is the coarsening of each thread, is equal to 1024. So each thread is calculating exactly the same as in the initial tile SGM. But the advantage of this register shared memory tile version is that it only uses 5 plus 1/4 kilobytes of on-chip memory. So even though there is a similar degree of reuse, it's 2 times more, it's around 2 times more efficient. And if you want to compare in more detail, like the reuses for data in M, reuses for data from N, the elements that are computed by each thread block, the amount of shared memory used, the amount of registers that are used, you'll see that the comparison is pretty favorable to the joint tile matrix multiplication, and actually the actual performance is also significantly higher, as you can see. These are results on the GTX 2080, which is the GTX 280, which is a pretty old GPU, but if you reproduce these experiments, these implementations in newer GPUs, you'll see that they are going to look kind of the same. So there is just one last question here, is how do we have to load data from the matrices efficiently into either the registers or the shared memory? There is no problem for matrix M. For matrix N, we can perform coalesce accesses to the global memory. For example, we can have 4 threads belonging to the same warp accessing these 1, 2, 3, 4 elements. So as you see, the access is completely coalesced because these 4 elements are consecutively stored in memory, but that won't be the case for matrix M. And that's because the way we assign threads to the output tile is by having different threads in different rows or different horizontal strips of this output tile, right? So when we have thread 0 and thread 1 need to go to matrix M, there is a stride between the access of thread 0 and the access of thread 1. And these strides, as you know, are going to cause uncoalesced memory accesses. There are different potential ways of dealing with this. One, say, a straightforward way is to transpose matrix M such that each of these columns becomes a row, and this way we can have coalesced accesses because consecutive threads will be loading consecutive elements from global memory. That's one possibility. Another possibility, a little bit more sophisticated, but doesn't require transposition, is to use the corner turning technique that basically consists of loading one entire tile into the shared memory first, and then from there read each thread will read individual elements from the shared memory and place them into the registers. And this way, all accesses can be coalesced and threads can access in a more efficient way the data. So in order to finish with the lecture, I just want to introduce an important library that is used by basically all machine learning frameworks these days, and it's a library that makes intense use of optimization techniques as the ones that we have introduced in this lecture. This library is codnn. codnn is a library of optimized routines for implementing deep learning primitives. It's an API that can be integrated into, or is integrated into, existing deep learning frameworks like Caffe, TensorFlow, Theano, or Torque, and similar to cuBLAST, codnn assumes that the input and the output reside in the GPU device memory. Just for a very quick example, let's talk about batch convolution, which is the most important primitive in CNNs. And there are 2 inputs for the convolution. One is the tensor with input data with the input feature maps, and the other one is a tensor with the convolutional filters. In the case of the input feature maps, we are going to compute mini batches. That's why we talk about batch convolution. So we have n images in the mini batch. Each of the images has C channels or C input feature maps, and the dimensions of them are H times W. As you can see, the naming of these different parameters changes a little bit with respect to the previous slides, so pay attention to that. And then we also have the tensor for the convolutional filters. That is also a 4-dimensional tensor of K, being K the number of output feature maps, C is the number of channels, the number of input feature maps, and R and S are the dimensions of the filters, the height and the width of the filter. Remember that we call them K1, K2 in the slides in the initial slides of this lecture. So the output is also going to be a 4-dimensional tensor that is called O, And the dimensions of these 4-dimensional tensor are n by k by p by q, being n the number of images in the mini batch and k the number of output feature maps. So for each image, we have several output feature maps, and in total we have n images. But where are these p and q coming from? Well, p is a function of h, r, u, and the horizontal padding that we are using. U is the stride in the horizontal dimension, and Q is a function of W, S, V, and padding on the horizontal dimension, in the width dimension. So height and width of the output feature maps depend on the input feature map and filter bank height and width, along with padding and striding choices. The goal of striding parameters U and V is to reduce the computational load by computing only a subset of the output pixels. So we are not computing all pixels of the output feature map, but just those that are at a certain stride, U or V, depending on what's the dimension, vertical or horizontal. And the padding parameters are for improved memory alignment and or vectorized execution. That's a kind of a padding at the end of the tensor in order to have better memory accesses, basically. So that's all for today. You can find more details about these use of advanced tiling techniques in the Programming Massively Parallel Processors book. If you have the 3rd edition, you can find this in chapters 7 and 16. And if you have the new 4th edition, you can check chapters 7, 8, and 16. That's all for today. I really appreciate your attention, and thank you very much for joining, and hope to see you in the next lecture.